Yeah, we will wait. I'll wait for a few more minutes. Yeah. Yeah. Okay. So we'll let a few more people join in. Okay. I'll start. Okay. So I'll start. So everyone can hear me? Someone say yes.
Yes, sir.
Okay. Yeah, you can see my screen, I'm assuming.
Yeah.
Okay. Yeah, here's an outline of today's lecture. So this is modeling part 2. What we will see today are, modeling sequential code with a program counter, a more systematic, automatic way of I don't see. Yeah, just hang on. I have to go to this. Okay. Yeah, got it. Yeah, sorry. Yes. So we had seen a way of modeling sequential code earlier, but we'll see a more systematic and automatic way of deriving a symbolic transition system for sequential code. Then we will see how to model concurrency, especially the use of non-determinism for abstracting irrelevant details there. And and we also see an important aspect of a consequence of using non-determinism to model concurrency, which will require us to look at a few something called fairness constraints. Okay, and these are all kind of, I'm laying the foundation here so that, or enough material I'll give you so that you'll be able to actually use one of the first model checking tools that we will be having you experiment with in this course called new SMV. And if I get through with all the material today, the next class will be a demo by Zubin in how to use new SMV. Okay. So here's what the way that we had modeled this simple four-line code. Okay, we kind of, we did not use PC. The state was the components of the state were just the values of the variables, the program variables. You would have wondered that, how come I did not use program counter at all. So what I'd done here was, I kind of thrown away the program counter because our focus was only to track the behavior of this code at a high level at the loop head. Okay? And therefore, I kind of threw away the control structure information almost completely, and I generated a transition relation for that described the effect of the body of the code in one step. Yeah, this kind of a method does, and I constructed it kind of magically, okay, by looking at the behavior and by understanding the, what the program was doing, okay? So, but as I said, what we need is, so we may have complicated control structures, in which case we may need PC, and also a method by which we can define the transition, piecewise transition relation for each statement in the code, and come up with a scheme by which we can construct the overall the transition relation for the entire program by composing the piecewise transition relation for the individual commands or in the program, and that's our intention here. Okay, and also do it in an automatic fashion so that it can actually be implemented. So what I'm describing today, or all of what I'm describing today, are, as I mentioned in a few classes ago, are part of the front end of a typical model checking system. All this thing is forms the front end where you describe your artifact that you want to verify in some language. It could be a standard programming language or a language constructed for transition system, and then it derives, the front end automatically derives a symbolic representation for the transition system in a sound and correct way. And that's what you will see here. First for sequential programs and sequential code, and then for concurrent programs. So let me start with this simple one-line code, which has a single statement. So as I said, we will be introducing labels, program counters, labels. So starting with the program here, we have, in this case, there's only one statement. Therefore, I introduce two labels, one denoting the entry point and the other denoting the exit point. Okay. So the variables that form the state variables, they include the program variables because we certainly want to track them, okay? And they also include all the labels that the PC component, the state variable component PC can range over. So my state is it's a tuple of vars and NPC. Okay, so first I'll define this simple function, a function that you will see we'll be using in the the derivation process, same, which takes a set of variables, okay, a set of state variables, and it denotes this formula. Okay, it just says that these variables that are listed in the set do not change. Okay, that is, they are, the S prime here corresponds to the post state, S corresponds to the pre-state, and they remain the same. Okay, so that's a shorthand that will be convenient for us to use in this translation process that I will be showing you. So as I said, what we'll be doing is that I'll be showing you a rule for each of the typical constructs that you see in a programming language, starting with the assignment statement, and then a conditional statement and a loop. And that is pretty yeah, so of a typical language. Okay, once you have a rule for assignment, conditionals, and while you pretty much have a universal set of things that can make any program, and that's the idea. So what is each of these rules defines the transition relation corresponding to that particular statement. Okay, a statement of that of a particular class. Okay, so C denotes the transition relation. Okay, function that generates the transition relation. It takes a pre-label, a label that is at the beginning of the statement, and a post-label, PC, to which you can go to, because some of the constructs can have change in control structure. So that's why we need a pre-label and a post-label, L and L prime here. And this is the general form of an assignment statement. And the formula on the right-hand side of the triple equal here describes the transition relation. Shows the transition relation corresponding to the that particular statement. So the transition relation is a formula that relates a pre-state S to a post-state S prime. And what this thing is saying is, if I'm at SPC, if a program counter at L, my label is L, and I execute the statement, then it is describing what the effect of the statement is. So S prime of X must be equal to whatever the value of E is in S, okay, in the pre-state. Okay? And all the rest of the variables in the all the rest of the state variables in the state will all the rest of the program variables, that's what bars represent here. So except for X will remain unchanged. Okay? And that's why I'm using same. Okay, and the program counter here will be L prime. Okay, which is the usually here it will be the one next to the program the statement in the overall code. So given this rule, so what would be the transition system? I'm going to use this rule to derive the transition system for this program, which only has a single assignment statement. Because the initial state is whatever the state of the variables at the beginning. In this case, there is an initialization statement, and therefore, so it states that the PC is at the entry point, and all the variables are program variables are initialized to 0. Okay. And the transition system is, it just has to invoke. The transition relation. The transition relation is if you're in an arbitrary state. Okay, it is going to describe. So that's what this thing is saying. So here if you are that there's only one entry, only one label here that is inside the program. So if I'm at at entry point, then I will do yes. So this S prime x is equal to that piece here is obtained by, I mean, this whole thing, as a matter of fact, is obtained by invoking C corresponding to the assignment rule for L entry and for an L prime exit. Okay, so because those are the two labels corresponding. So this is the transition system. So you get the idea, correct? Right? I hope. Yeah. So that's how. So what I will show you is what the rule for deriving the transition system for each kind of statements. From that, you can instantiate that rule to then derive for the entire program. So here is a program that illustrates how you derive when your program is a sequence of two commands. Okay, two commands. Okay, so here, yes, there are only two statements. So in general, you can have a complex program structure there. Okay, so this is defined by using this following rule, sequence rule. Okay, so in general, so this is the sequencing statement takes two commands, command 1 and command 2. Okay, and yeah, as I said here, when we don't have labels, the first step of this process is to introduce enough labels at the beginning of every statement here, and that's what is done here in the program. So what I've done, sorry, here. So from here, there's no intermediate label. There's only starting with an entry and exit. I'm introducing an intermediate label for the second assignment statement here. After that, so this is this sequence rule is defined in the following way. So given an entry label and an exit label for this entire for this program constructed by the sequence, then you have two subcommands, command 1 and command 2, and an intermediate label. It is defined in terms of that. Okay, it's a disjunction of you apply the C recursively to the left command, command 1, and left command 2. The first command, the pre and the post labels are L and L inter, and the post command is for the command 2 it is the intermediate label and the post, and that's how you derive. Okay, so and applying this for the program that this rule for the program show. So what is the transition relation I get, and that's what I've shown here. Okay, this is pretty much what it's saying is, it is saying if I'm at, see, I mean, when you're executing this program, so you are either at one of these three labels. So you're at the entry point or L. Okay, if you're at the exit point, there's nothing to do. So what this does is it says the first, it's a disjunction of two formulas, where the first formula describes what the transition relation have to behave like when you're at the first entry location, and the second one is saying what you will have to do at the second location. So, and that's what this thing is doing. So since each of them is an assignment statement, I'll be using the assignment rule and I'll be deriving. As you can see, what the first component is saying is if I'm at the entry point, if my PC is at the entry point, then I'll be, the transition relation should be describing the effect of executing the first statement, which is x is equal to x plus 1. Okay, and that does just states that the value of x in the post state is x plus 1. Okay, and Y and Z will be unchanged. And your PC will be set to the post label corresponding to the first statement, which will be L. Okay, I mean, which will be L in this case. So L will be standing in place of L inter. And yeah, so you get the second one once again by instantiating. I mean, yeah. So calling C for the second statement, and this states that if I'm at L, which is the label for the second statement, then the transition relation should describe what happens when you execute y is equal to x plus y. And that is what's saying. So in the post state, the value of y should be whatever the value of x and addition of x and y, and x and z remain unchanged, and your PC will be set to exit. Okay, is that clear? Or any questions? Okay, then I'll move on.
So this is how we have modeled the program, right?
Correct. That's the transition relation corresponding to the program. See, the transition relation here corresponds to one step of execution of the program, one instruction. Okay, in the program based on where your program counter is at. Okay.
Okay.
I have a question regarding the state space. So the state space is all possible values of all the possible variables that the variables can have, right?
Correct.
So it can be an infinite state space as well.
No. So as I said, yes, in this case, PC will be ranging over only a finite set of labels because my program is finite. Okay. So the PC will be ranging only over, because as you will see, we are associating label for each statement. Okay. So since the program is always finite, that is finite. Vars, the program variables, can range over infinite domains if you do permit infinite domains. As I said right in the beginning, here this course is model checking of finite state systems. So so given that, we will be precluding infinite state systems, but for argument's sake, if you're allowing the variables in the program to range over infinite states, it'll be infinite. Okay. But yeah. So does that answer your question? Yeah. So yes, but given that this transition relation is giving you the behavior for an arbitrary state. Okay. If I'm at an arbitrary state, if the program is at an arbitrary state, by an arbitrary I mean the program variables could be anything, and which means that the PC could be in any one of the possible values it can take. Here, there it can only be in one of these, in this case, one of these three things: entry, L, or exit. So, and I'm, so the transition relation is specifying what the effect of executing one instruction that is pointed to by the program counter in the program. So if you want to now express your effect for the entire program, you have to, of course, have, invoke T, okay, several times, as we will see, okay, later on. But this is, as you know, because it is telling you exactly what to do when you have, PC is an entry and an L. Of course, it is not. What is missing here is what happens if you're at the exit point. Okay, so what I have. Okay, that's it's good that came up. Okay, so although that is missing here, the implicit assumption is if if PC is at a point which is not described here, then nothing changes. You could say it is the same on all variables as well as PC. Okay, so technically, strictly speaking, I should have had a disjunction corresponding to the case where s.pc is an exit. And as we have said, for all terminating programs, I had indicated that we will assume that it will stay in the same state. Okay, so that is the default assumption. If you strictly want to make this complete, there has to be a case for PC is equal to exit, for which it'll be same on all the variables, including PC. Okay. Okay. Now, how do we take care of a conditional statement? Okay. So in the conditional statement, we need to. There is a control structure change. In the previous case, it was all sequential control. Here, depending upon the Boolean, whether the condition is true or not, you either jump to the then part or the else part. So to model that control thing, we have to introduce two intermediate labels, one corresponding to execution of the then part, and the other corresponding to the execution of the else part. And so two intermediate labels have to be introduced. And given that, the conditional rule is described on this labeled program. So given a pre-label and a post-label for the statement. And now if for an arbitrary conditional statement, which has some arbitrary command 1 and command 2, okay? There must be a space here, yeah. So, so here the labels are elif for the if part and else for the second part. So all it's doing is, okay, so it has, four components, disjunction of four formulas, which are conjunctions. The first subformula is saying what happens. Okay, it is capturing the control transfer from L to elif. So if I am at L, which is at the start of this if then else statement, and if C, the condition is true, then my post PC will be elif. Okay, so my control location changes to the then part. I'm sure I should have had it as then, I guess, here. So yeah, to elif, and nothing changes because the just evaluating the condition doesn't have any state change, and that's why all the variables, and the only change it has is change in control, which is described by change to PC, and all the program variables remain the same. Or if I'm at L and the condition is false, then PC has to be moved to the else statement, okay, and no change in variables again. Or I could be in one of either at elif or else, in which case I'll have to do whatever. The transition relation will be corresponding to whatever the transition relation as per the rule is for corresponding to command 1, and with my post control location being L prime, okay, which is whatever is what is given to this CL statement, which is the post of the entire post label of the entire command. Okay, so whether you execute the then part or the else part, you will be moving to the same post label, and that's why both these recursive invocation of C are having the same post label. Okay, L prime. Now, as an illustration, I'll be instantiating this rule to derive the transition.
I cannot understand why this is disjunction and not conjunction.
See, there are ways of doing it. You should read this thing as, since, yeah, obviously it can't be conjunction, because if just imagine if it's a conjunction, see, you're at any point when you're executing the program, you can only be in one of these locations, entry entry, which is the enter command, or L1, L2, or exit, correct? So if you put, you see, this is almost like an implication. If I'm at L, then this thing. If I'm at LF, then this thing. Okay, that's how you should read. And then I have converted them into kind of a DNF notation. See, if you did an AND, okay, what would happen? It would be unsatisfiable. You can't be at the PC cannot be at the same time at LF, LLs as well as at the thing. So each.
I mean, it should be conjunction of statement 1 and 3 and disjunction.
Yeah, but that has the same effect. Okay. So if you look at this for this program, okay, just okay, this is the result of. I'll explain to you why a disjunction in this form gets you that that effect. Okay. So as I told you, you can only be in one of these things. Okay. So if I'm at entry, then my S prime will be as per the first conjunct. Okay. So I can only be, so I can be at entry and this condition can hold good, or I can be in entry and the negation of that can hold good, or in the process of arbitrary execution of this program, I could be at L1 or L2. Okay. So in that sense, it is, you can only be, your PC value can only be one of these things. That's why the disjunction comes. Okay. Now, you could state this in other forms as well. Okay. In this form, if you had a conjunction, you will see why this whole thing reduces to false, because S.PC, it cannot be at the same time at entry as well as, okay.
Okay, I understand.
So let me, this is the fully expanded version, okay? So if you did an AND here, conjunction of the whole thing, then it is not. Then you cannot have PC to be the pre-PC to be simultaneously at one of these, in which case you will have to have implication, okay? There are two ways of describing it. Either you say, I'm at PC is equal to entry, then this happens, then you can have conjunction, okay? That's another way to state it, okay?
Okay.
Yeah, but here I'm stating it as a disjunction so that when you're at a particular point, particular location in the program, what will happen, all but one of them will reduce to false, okay? And therefore you get that, the effect, yeah? So you're right that you could be with the, you can use conjunction, but in which case you have to have implications. If I'm at this PC, then something kind of form. So I've just stated it in this fashion. Yeah. So this is the fully expanded version of the transition relation for this program by applying by recursively applying C to each of the else and the then the part. So the first two correspond to the case of control transfer, in the case where the condition is true and the case where the condition is false. Okay. So I've expressed it as x less than or equal to 0 or x greater than 0. So there, none of the variables change, only the control location changes. And the third and the fourth correspond to the transition relation describing the behavior of executing the then and the else part. Is that clear?
Yes, sir.
Okay, so if it's clear, I'll move on.
Yes, sir, it's clear.
So here, this, to ensure that you are going through the thing. So I will now illustrate, it's the same example as I had in the previous slide, okay, with the transition relation that I showed. I'll tell you how we could use this transition relation to get the a symbolic expression which describes the effect of executing this program from entry to exit, okay? Completely. Remember that you know, in the Z3 demo, we'd already seen how you repeat, you can construct formulas to denote some kind of an execution of your system over multiple transitions. And that's what I'm doing here, okay? So, you know, if you want to get the effect of executing this symbolically over the entire program, then you will have to have appropriate number of repetitions or a copy of T. Okay, so this is what is generally called symbolic execution. See, it's different from, it's kind of running your program, but you're not running it on specific inputs, but rather on formulas that describe sets of states. So in that sense, it's a symbolic execution of over set of states. In this case, it happens to be, because my initial state is a single state. Initial set of states is a singleton state. It is kind of equivalent to execution, but you can imagine that doing this starting from an arbitrary state. So what I want is to see what the effect of this execution is starting from the initial state as described by init, and execution, the whole thing. So I need 2 instances of T here, because as you know, there is one jump from entry to L1, and then another jump from L1 to exit, okay? Because the evaluation, that control jump is described as a separate step in my transition relation. And that's why in order to get the effect of executing this program, I need 2 things, okay? So if I can, so this formula here, init s, T of ss prime and T of ss double prime, will, in s double prime, will give you the effect of executing it starting from the initial state. So so instantiate this. I'm expanding init, okay? Then I've expanded here Ts of s prime, okay, as described. And you see, this is kind of simplified, although this has, like, lots of disjuncts. For this particular initial value, since I'm at PC at entry, and the initial state is such that s dot x is less than or equal to 0, this is the only statement that is non-true. I mean, I'm sorry, non-false. All the rest will, simplify to false, correct? Because this says s dot pc is an entry. So, and this is the only thing, and that's what is remaining here, okay? And I have T s prime s double prime. Is that clear?
So in this case, the if condition just resolves automatically.
Correct.
But if it doesn't, we might have an explosion of, like,
yeah. I mean, you will have an explosion in the sense that is if you're executing it this way, okay? So you're right. So you will have, as in the worst case, nothing might simplify. So if you started from an arbitrary state, then you could have the, you could either have the else part triggering or the then part triggering, in which case you will have a disjunction sitting there, okay? You will have a disjunction. So you're right that if it's represented this way, yes, you will have, but in the worst case, you will only have, if for a certain number of bounded number of steps, it will be linear in the formula will still be linear in the size of the original formula representing T, okay? Correct? I mean, in the worst case, you can have all 4 of them. So, I mean, you could say that there's an explosion, yes, but it is still linear in the size of the formula denoting T, okay? But you're right that for, how do you, if this is the way that you're doing model checking, then there are some things, you know, you don't know how long, how many instances that you will need, okay? But I'm only using this for illustration, yeah?
Yes, I see. So it will be linear in the program's total program size.
Size, correct, yes, the resulting formula.
Right,
Okay?
right, okay.
But still it will be linear, that's the, so, and then now I've replaced T S prime S double prime. Okay, and since X is, yes, less than or equal to 0, therefore only L1 will apply, L2 will not be there. So this is the case for L1, and I've simplified that to true here. So yes, strictly because S prime PC is L1, everything else, in this instance of T S prime S double prime, everything except the part corresponding to the then part here. So the third component will be will remain, and I'm at exit. Okay. So any satisfying instance of this simplified formula, specifically what you have in S double prime, will give you the output, okay, of your program. So I showed this only to convince you that indeed the that it captures the semantics of your program, that is the program behavior accurately. Okay. Yeah, I've just simplified it further, I think. I've just expanded the same thing out and obtained the full formula. Okay. So yeah, so let me move on. So the remaining and kind of interesting case will be for the while, okay? For the while, this is the unlabeled version on the left. So the labeled version, I will introduce, since the body will be executed repeatedly here, so I already have the label, pre-label for the entire statement, the while statement. I'm introducing intermediate labels, a pre-label for the beginning of the body, and in this case there are two statements, and therefore I'm also introducing the intermediate label for the sequence. Okay. So so that you do, but the while the transition relation for while command itself is just stated in terms of whatever is the, in terms of, it's built from the transition relation corresponding to the body, okay, given a pre-label and a post-label. So there are three cases here to consider. So I'm at the pre-label L, and if my Boolean condition, loop condition is true, I enter the loop, okay? Therefore my PC is set to L body, okay? And nothing changes. Or else my PC, I'm at L, and if the condition is false, I exit the loop, in which case the PC will be L prime, and variables don't change in this case either. Otherwise, I execute L, the body. With the pre and the post. See, I execute the body. I replace it with the transition relation corresponding to the body, with the pre-label as at the beginning of the loop body, L body. And the post, after that, I have to completely repeat this. The effect of the transition relation will be the same thing as for the entire while loop, and that's why. So I'm putting as the post label L itself.
The last rule is a sequential rule.
This is a sequential code, no? So what do you mean by sequential? This one is, yes. I'm sorry. I'm not, yes. I'm moving to, yes, this would be, which is the sequential rule? I mean, that depends on the body, no? The body can have sequential. In this case, it is sequential. The body can be an arbitrary command. That itself can be another while loop, okay? So it can be anything, yeah? So, but what I'm saying is, I have to replace the transition relation that I get for corresponding to the body, okay? So, and this recursion always terminates here because I'm using the structure of my program, correct? Eventually, I'm not executing, C is not executing. It's not a dynamic execution, but rather it is recursing down the structure of your program, okay? Therefore, eventually, it'll come down to the assignment rule and it'll stop, okay? Yeah, let's see on this example, which should hopefully be make it clearer. See, because what I'll have to do is see the post label is L, because each time I have to this might be no, I think this should be so let's see. So there's a bit of something wrong here. Yeah. Well, I should actually have an if then else. Okay, maybe that was your comment. Okay, so there should be an if of this. Yeah, this B should be not just the body. I should have an if then else kind of thing. Yeah. Yeah, but by making it as C of if then else to L is what I should have. So then I will have this whole thing. So for example here, if I'm at entry and if X is less than 10, then I will go to SPCL1 and everything will be the same. If I'm entering if exit condition holds good, then I exit. Or I'm at L1 and it's the same thing. So yeah, so then I will execute the body. I think this is fine. Okay, so then I will get to, I will go back to at the beginning of the body. I think this should be L body, okay? Because after executing B, I will go to L body, and that's what this thing should be. Yeah, yeah. So I'll be recursing down this command, and I'll have here I'm invoking it with not with. I'll be invoking the C with L corresponding to L will be entry, L prime will be exit, and I'll only have L body, which is L1 is what I will be having L body. Okay, so yes, and this should be, I'll be going back to executing L body. Okay, that's what this thing should be, or the if then else. Yeah. Okay, so yeah, so that's the idea. Okay, so if there are no questions, yeah.
Yeah. So in this case, we did a symbolic execution for if then else, but we cannot do something similar here, right? Because we don't know how many steps this may or may not take a priori.
Yeah, but that's why the mistake here is I'll have to have the transition relation. See, this transition relation, there's a bit of a mistake here. So from L body, I'm going to L, okay? I mean, and this should be the while, yes, you're correct. Yeah, yeah. So you can do for finite number of executions. Yeah. I know, but what you will be. Right. Yeah, yes, your execution will have an indefinite. Yes, there's no finite execution. You can do that approach for bounded executions. Okay,
I see.
but that's not the only way to do. Okay, when you do model checking, we'll be computing fixed points. Okay, that by in a way that uh, uh, you know computes in a way that because if it's finite state, okay, strictly speaking, you will have to keep on repeating this until you reach what is called, you're not accumulating any more states. Okay,
Yeah, okay, I see.
that's how you do model checking. You're right that the number of steps that you need in order to execute it is not is not known. It's a function of your initial state itself. Therefore, it's not known. But that is where the crux of the model checking algorithm is. Okay, if you were doing explicitly enumerating the states, then you will end up enumerating all of them. Okay? But given that you're assuming that it is your transition system is finite, you could use the trick, I'll keep on applying T until I don't add any more new states, something like that. Okay? That is how we will do. You will see model checking will always be expressed as like that. Yeah.
I see.
That's a good question. It's like a forward-looking question, and that's how you do. And then you can check those things. Okay. So whether you saw how you could compute image computation. If the image that you compute is already included in your already accumulated states, you stop. Okay, something like that. Yeah. Because that's why for finite state system, there is always a way to do it. Yeah.
Okay.
And how you do that efficiently is the crux of model checking, is the symbolic model checking. Okay, so yeah, any other questions there? Okay. So I will now switch to, with that background of sequential, encoding of using the PC, we'll get to concurrency. Okay. See, when you're dealing with concurrent systems, there are so many different forms of concurrent models. I mean, concurrency mechanisms. Okay, that are used. For example, there is shared variable concurrency. There is concurrency in hardware, multiprocessor systems. Okay, that is one kind of concurrency. There's is very ubiquitous. So you can have multi-threaded programs of the kind that you see in Linux. You can have distributed protocols, and you can have message passing systems that communicate over channels and probably unbounded channels and so on. They all have different semantics, but they do have one thing in common, that there are several actions initiated by processes that happen simultaneously. How they synchronize with each other, in order to communicate with each other, to synchronize the parallel actions among the processes, is what varies in these things. And sometimes one can be modeled using the other formalism. To keep things simple, we will be concentrating on modeling only one kind of concurrency called shared variable concurrency, wherein the different processes communicate via shared variables. Okay. And this is fairly fundamental. Okay. And a lot of other kinds of forms of concurrency can be modeled and expressed in terms of shared variable concurrency. The other forms are much kind of a higher level forms, where you don't want to make everything implement in terms of shared variables. So in this form of shared variable concurrency, there are two kinds of communication paradigm, which we will be looking at: the synchronous communication paradigm and asynchronous communication paradigm. So our modeling scheme, the symbolic modeling scheme, will differ for these two things. So you see the synchronous kind of systems in hardware and embedded control software. So here there is the assumption of a global clock. All the events are synchronized as per using a global clock. In hardware, we've already seen that the clock is what every tick of the clock determines the transition system, but you can have multiple pieces of hardware which are operating at the same time, and you know, they yes, they do as per the clock. Even in embedded control software, there is a global clock, although it may not be explicit as in hardware. The thing in embedded control software, it is determined by the environment. Okay, every time the environment changes, everything, all the concurrent components inside the software change as a reaction to the input. So there, the time is actually, the notion of time is change in any one of the environment variables. So environment in any variable in the environment. So that is you know, appropriately modeled. I mean, they are typical synchronous systems. Asynchronous systems you know, represent that communication paradigm which is more suitable for software. Okay, you know, software processes running on an OS. Okay, so like you know, forking. You know, you have forking and C11, P threads, and those kinds of things, or even you know, software communicating over networks with synchronized communication. Okay, so through message passing with channels which are bounded. Okay, all these kinds of things can be you know, usually use a paradigm of communication called asynchronous systems. There is here, the scheduler is a little bit more complicated, and it takes actions. It determines which process in the system to schedule next. Okay, so we will concentrate on these two kinds of systems, and then I'll show you how to model them. Okay. By the way, I should mention, I don't know why I had footnotes here and they're not showing. Maybe. Yeah, but these things I'm following the book, the model checking book, which I have a link to fairly closely as far as this chapter is concerned. And I had footnotes. I don't know why it's not visible. I will check on that. You know, that gives the corresponding sections there. Okay, so you'll see both these things, how to. Okay, remember, you recall this example that I had of a hardware, the mod 4 counter. What you see on the right side here was the mod 4 counter, in which, yeah, it counts. It has a resettable mod 4 counter. So the second component here is the input, and we said that we'll be modeling inputs as a non-deterministic entity, I mean, whose change is non-deterministic, and will incorporate that as part of the state. Okay, and that's where you have in each state the second component can arbitrarily change to either 1 or remain 0. Okay, so this is what this thing you know, is. Here there was one. Yeah, so there is, yes. I mean, in this, for the purpose of this particular example here that I'll illustrate, you should consider that both this can be an input, I mean, in input state as well as this one, because the environment input state is one in which the counter is initialized to 0, but the environment on which it does not have any control could be either 0 or 1. Okay, so I'm going to illustrate what synchronous composition is before I give a formal definition for it. By illustrating how this thing can be composed with an environment to have a closed system. Okay, so here is what is on the left side is an environment that is generating the reset signal, which is an input to the open system on the right side. Okay, so I made a mistake here. Okay, so just cross the this part out. Okay, so this environment is generating continuously generating reset. It's just generating a sequence of zeros. Okay, and this, so it's outputting zeros, and I want to compose this, the one on the left side, the environment, with the system on the right side, where the reset here, which is the output of this system, corresponds to, is matched up with the input, which is the second component on the right side. And so here I consider both these systems to be governed as synchronous systems. They're marching as per a global clock, and I want to compose this thing. So that's how this parallel, concurrent systems are. The transition system derivation is expressed that way. Okay, as I said before, for a sequential code, we did compose a transition system for the entire program from each statement. So here we have two, assuming there are transition system for two components, which are composed, which use either synchronous or asynchronous concurrent composition to build a concurrent system. So we want to compose these two things together. Okay, so so the symbolic description of the transition system for the mod counter is described here. Oh, there's something wrong here. No. I have mixed it up. Yuck. Yep. Okay, so I have completely screwed this thing up. So you should read this as this should be TS mod. Okay, the second one. This is describing the TS mod. Okay, this TSN here should be TS mod, and the init is init of N is true. So N and mod has to be switched. Okay. Yeah. So please. So what is described as TS mod actually describes the environment state machine, and what is TSN describes the modulo counter. Okay. So in any case, so that's what this these two things. So synchronous composition, informally it consists of this thing. So it's a way of composing the two things, and the concurrency here is described in such a way that you start each system with the respective initial states, and you march both of them in lockstep. Okay. So because, as I said, it is governed by the global clock. So at each time that that global time advances, the both the transition, every component in the concurrent system is advanced. Okay. So you march both these systems in lockstep. Okay, and that's what is I'm doing here. And of course, you can have there's input-output correspondences would be there. So you have to there can be some inputs going across the two things. In this case, the output of the environment is going into the right side, and that's and you'll have to match up that thing by certain equality constraints. Okay, and that's what we want to model And we want to model that kind of a synchronous lockstep synchronizing behavior. And given that paradigm, we want to see how we could construct a transition system for the combined system that accurately describes the effect of lockstep synchronization. Is that clear? So what would be, informally, so given that lockstep thing, so what would be the behavior of this combined system here? Anyone would fathom to guess? See, I'm restricting the environment, as if you can see, this environment is generating just zeros. Reset is always 0, okay? So if I'm feeding only zeros here, what will this be doing on the right side? It'll just be continuously, it'll never get reset. It'll just circulating the counter from 0 and wrapping it back to 0, okay? Whereas this, if this environment was different, then your behavior would be different. Did you get that? Hello? You guys there?
Yeah.
Yeah, okay. Yeah, so in general, what we have is two systems, and composing them in a synchronous fashion with some inputs going either way. It consists of this kind of a composition. So the state of the combined system is a cross product, so of each of the components. Okay. So the composed system will have, it's a cross product of where the state of each component is included separately. And the, so each system will only modify its component of the state, okay? And except for the only interaction will be between the inputs and outputs that are going crosswise, okay? So this, and as I said, at each step, both the transition step of both the systems are marched, and therefore the transition relation of the combined system, TSS prime, will be just like equivalent to taking a conjunction, because both of them are advanced. Both the transition relation are done on each of these each of the systems. Okay. Therefore, of course, each of them will be only changing their component of the thing, and that's why this TI is defined as the first part takes the entire global thing, and the second part takes SI. So the reason the new state of some of these systems can be dependent on this state, but it will not be changing them because there are some outputs that it is consuming from the other system. The output is usually a function of the current state and inputs here, and that's why each TI applies the yes, takes the entire state, and it only modifies its part of the state. And the lockstep thing corresponds to doing a conjunction, because you want the next state to be consistent with the behavior where every transition, every process here is marched ahead, and that's why. So the initial state will be should be one in which each of the components will be in its own initial state, and therefore that's also a conjunction. And no, this should be just T, okay? T SS prime, as I said, T synchronous will be, yeah, the T with IO will be exactly this T SS prime with input output constraints. What do the input output constraints say? That it just has to say, just like I illustrated in the previous case, the input has to be, you know, in the case, the reset component in one of the things corresponding to the reset in the other ones. These are equality constraints that you have to express to match this. I mean, to describe the correspondence between input and output between these subcomponents. Okay, so what is the effect of the symbolic formula representing the composed transition system here? So once again, I'm sorry, this should read TS mod. Okay, and this is init mod is correct. Read this as TS mod, and this should be read as TS end. Okay, and that's you know, that's a mistake. Okay, so initially you start with reset negated, and you keep the reset the same. Okay, so as you do it. So the composed, synchronously composed transition system, its state variable is just the cross product of the two. And the initial state for the combined system is defined as a conjunction of the initial states of the two component systems. And with the constraint that the reset here should be the same as the reset component, because that input is fed directly as, that output is fed directly as the input. And my transition relation for the combined system is just a conjunction. You see, so it's fairly easy to construct the symbolic representation. All you need for synchronous composition, it's just taking a conjunction of the corresponding transition relation for the two things. Yeah. From here, I'll take the S1 part, and from here, I'll take the S2. Oh, actually, this should be S. TS, this is the S1 prime, and TS, S2 prime. And you know, the input correspondences have to be asserted, okay, which is what I'm doing here. Okay, so the simple message here is synchronous composition can be, when you're modeling it symbolically, it just corresponds to conjunction. So it's a fairly easy thing to do. So any questions there? Okay, so let me move on. Yeah. Okay. So what is asynchronous, you know, communication in concurrent systems? Now consider here, this is a multi-threaded program. Okay. I mean, C11 program where you fork into 3 separate threads. Okay. So what do you expect the output, to be? I'm claiming it is X is equal to 11 and Y is equal to 21. Is that the only possible output when I execute this as multi-threaded software? So one of the things here is that these processes have shared variables. Here, both X and Y are considered to be shared variables. That is one thing different when you're doing software asynchronous composition. There, in synchronous composition, each of them modified its own state. They could use inputs which are function of the other component state as inputs, but they were only modifying their own component, whereas here there is some shared component which each of them can be modifying independently. Okay? So that's why I asked you the question based on your understanding of what multi-threaded thing is this the only output that is possible?
No, I mean, y can just come out as 20. I think x can also just come out as 10.
There are multiple possibilities, because what typically happens here when you run a multi-threaded program, there is an implicit scheduler which the OS implements, which schedules each of these threads, okay? In using its own scheme of things based on priority and various other things. And it interleaves, okay, the basic atomic steps of each of these processes, somewhat, as per its scheduling strategy. So here the atomic steps, assuming the atomic steps correspond to statement boundaries. So what, there are multiple things possible here. Outputs are possible depending upon, corresponding to different ways you can interleave the execution of statements among these three processes, statements in these three processes. Okay, so that's the kind of behavior, concurrent behavior with asynchronous composition that we want to, asynchronous semantics that we want to model. Okay, so overall, what we have is each process state, although it's not shown here, is allowed to have a local component which it modifies by itself, and a shared component. Here, everything is shared, which any one of the any of the processes can modify as part of their atomic step. And the model the model of concurrency corresponds to interleaving of process actions, which is consistent with OS scheduler. So how do you model this thing? So without the scheduler, how would you model this? See, so this program, yeah. So how would you model this? Either you have to model, in order to model this faithfully, you will have to include the scheduler also as a process. Otherwise, how would you model this? Okay, but we want to be able to model this by hiding the scheduler. Okay, and that's the that's the goal. Otherwise, so for example, yeah, so because typically, since that is not known, the strategy adopted by the OS, the scheduler is not known, one has to, if one is writing a concurrent program, one has to either make it oblivious to, in general, you have to make it oblivious to any schedule that can be used by the OS. And if by, design, I mean, if by, you have no choice but something you want to, control for shared resources, you might have to have some specific synchronization primitives to, block access, to make sure that access to shared resources are done in a exclusive fashion. Okay, so so there are two things. Okay, so we want to be able to model this independent of the scheduler. Okay, that is one of our goals, because typically we want the behavior of this of a concurrent asynchronous concurrent program to be independent of the scheduler. That is another where non-determinism comes in handy. Okay, non-determinism is a very powerful feature to hide the scheduler details, and that we'll see how we will do that. Yeah, another component, another thing that you will have to be aware of when you're modeling asynchronously composed processes is to decide and be aware of the granularity of the atomic actions. So in this case, we used the statement level, but that's usually what it is, but it can be finer or coarser, okay, depending upon. For example, if you separated an assignment statement here consists of reading the variables and the setting, reading and writing the variables. Okay, one level deeper if you want to go, those two actions are also, the statement don't have to be atomic. So if you want to model it at that level, there'll be even more interleavings that are possible. So the point I'm making is the granularity of atomic actions, determining that is important in modeling asynchronous concurrency. Okay, so I'll just take 5 more minutes, and I will end today's thing. Okay, so modeling asynchronous process with shared memory. So here, your the component of the combined system will have to have all the local states. It must include the local states of each of the of the process component, and the shared variables will have to be included, but as a single instance in this S. So S here consists of the union of all the local state variables and the variables corresponding to the shared variables as well. And in order to model this thing of the schedule can be arbitrary. So here's how it is modeled. So we allow only one process at a time, okay, to march ahead. Whereas in synchronous composition, every process was allowed to march ahead. Here, because there are shared variables, here the model allows one process to think. So that's what I mean when I say you follow an interleaved semantics. Okay, so and that can be modeled by saying there exists exactly one process in each step of the combined system. In the combined system, only one of the process is allowed to march ahead, holding all the rest of the process in the same the state. Okay, and that could be the process that you allow to march can be arbitrary. Okay, that is where the non-determinism comes. So you can either state it. This one way of stating it is saying there exists in the next state. The next state corresponds to picking one of the sub-process to march ahead, holding all the other things in the same. Okay. More explicitly, this existentially quantified thing can be stated as a formula in this fashion. So the combined transition system TSS prime is doing, effective TS1 S1 prime, okay, and keeping all the variables in the rest of the process. Here I have this component here, this disjunct here corresponding to the case where I have selected process 1 to march ahead, okay? Then all the rest of the variables in the other processes will have to be the same, okay? Or it can be one other process, okay? There is one disjunct corresponding to every process here. So that's what this thing does. So as you can see, when you use an OR, there is natural non-determinism. We can be in a state where you have where you have simulated the first process or the second process or one process, the third process keeping all the rest of the process the same. So this is exactly interleaving exactly one process at a time. Okay, so this is how it is modeled. Once again, here also you see how you can construct the symbolic representation quite conveniently using as a logical, in terms of the logical connectives, in terms of logically, using the logical connectives to combine the transition systems of each of the processes. Okay, so I will stop here. In the next class, I will illustrate this, the asynchronous composition in more detail on an example, and hopefully that should make clear, any of the doubts that you may have, and some of the implications of hiding the scheduler completely. Okay, there will be some implications in terms of the behavior that will need to be aware of when you're doing model checking, and that is what leads to the fairness constraints. Okay, and that I will motivate and explain what the thing is. Okay, so I will conclude my part here, and I will open it for questions. If you have any questions, yeah.
So can you
It's not a
from what reference is the material that you are taught today?
None of them have this. Okay, these are all in. Okay, it's chapter 3, okay, of the model checking book.
Okay, sir.
It is chapter 3. I think it is 5, 6, and 7. Okay, even the sequential composition, the method that I've used, it's from there. So this material is pretty much faithfully follows that chapter. Okay, chapter 3. So I will make sure that the slides are updated with the thing. We will update it with those references specifically so that you will have. But the chapter 3, I don't remember the exact sections, but it's chapter 3.
So I had a question. So
Yeah.
In like real life multi-threaded systems, for example, when so certain operations are performed truly concurrently. Like, so if you're acting on, say, exclusively on local variables, then they are happening truly concurrently. But then we are still modeling even those operations as if they are happening one at a time. So I mean, is there that is still equivalent? Is it?
Yeah. Okay. So as long as even in those cases, they can all be simulated with this interleaved semantics. Okay, is what I claim. Okay, because if for optimization purposes you do allow individual processes to modify some of their local variables, they'll have to, you should allow them as long as they're only truly dependent only on the other local variables, okay? So you should not be making them, I mean, if one local variable, see, otherwise it won't be sound, okay? So there will be some constraints on what, you can only allow the local variables to march ahead as long as they're not dependent on the global variable. Okay, because if you do that, then you will end up creating data races. Okay, because you don't know while you're doing changes to the to the local variable, if the changes you're making, the values that you're assigning to them are dependent on the global values of the global variables, then you don't know when you do that whether they are consistent with the global variable that is actually being changed, right, by another process, correct?
Right. Yeah.
Therefore, though you typically don't allow those kinds of things.
Yeah, I mean, while actually programming, we avoid that. But then, if we were to try to say model such a program in this manner and actually run it, will we get exactly the same set of possible behaviors?
Yeah. If as long as they are, yeah. So what you think is, okay. So here it doesn't even allow that. Okay. So it only picks one. It picks one process to do its actions, including whether it's local or global. Okay. Now, if you want to allow that twist, that thing to model only under certain conditions, I do that. Then you have to change your interleaved semantics. Here I used a simple disjunction with a constraint. You will choose exactly one to process. Now you will have to relax that. Okay. So yeah, I mean, yes. So because that is, you have to, if you can only allow modification under certain conditions, and if you want to faithfully reflect, either one way is to make your composition operator, the way that you do derive this thing, reflect that restricted condition under which you allow local variables. Okay, that has to be explicitly modeled. In which case, the two will exactly correspond. Okay? Otherwise, if whatever verification that you do in here will be a true reflection of the verification in the other condition only if the other program you faithfully follow that restriction. Okay?
Right.
So your verification then, if I use this model, cannot be held. We will hold water only under the assumption that the actual program does what it is supposed to, with that restriction. I think a safer thing to do is, if you allow that, I would modify this composition, relax this composition operator the way I've defined to reflect that relaxed constraint. Okay.
Right. So in general, that is to reflect
Exactly
a system
right.
which allows that. That is what we should do.
Yes, that's how we should do, and that's how it is done. Okay. As a matter of fact, don't take this definition of asynchronous interleaved semantics, the way I've defined, as something cast in stone. Okay. Because there are variations of these things that you want to implement. Okay. There are even variations in terms of memory models. Okay. Sometimes the memory models here I'm using, that they're all performing at a certain level of atomic action.
Right.
That is more relaxed. Okay. In real systems. So therefore, you may want to, all that will require you to change your composition, your definition here. Formal definition is composition. Okay.
Yeah.
I mean, you have to be very, very careful when you do these things. And I think the way it's done is you include the desired behavior, the desired semantics in the way that you derive the symbolic formula for your composition. Okay. For your basic. That you have freedom over. Huh?
Right. Okay.
Any other questions?
It's not a question, but the more finer we have a statement, we'll have a blow up in the size of the formula, right?
The more, no. See, okay. So next time I will talk about various ways in which this model checking problem, or at least some very typical ways in which this model checking problem can blow up on your face. Okay, in terms of that's called the state explosion problem. Okay, so but the level of atomic actions, I mean, you can blow. There can be so many different kinds of blow up. Now, the level of atomic actions, that in itself may not be the cause. It is the way that the interaction, okay, between the way they interact with other actions from other processes. Yes, if you only have two actions that you can do per process. It's all exponential indeed. The number of kinds of actions that each of them can perform. Okay, you can, yeah. So in that sense, the more action you have, the more actions, the more deep lower level that you go to, there'll be more actions, and therefore the interaction semantics, the interaction, the interleavings that you have to explore will be exponential in terms of the number of actions. So if you increase the number of actions, that will have an impact, yes. Okay, but it is exponential in any case. Okay, so so sooner or later it'll blow up unless you use effective encoding techniques and abstraction techniques to deal with it. I will talk about those, in one slide next time. I have a slide. Okay.
So introducing non-determinism itself gets a blow up.
You see, no. See, introducing non-determinism by itself is not the thing. If you don't introduce non-determinism, then that will not have any. It can actually help you, because otherwise, here when you introduce non-determinism, yes, you do have it. Okay, it depends on the property that you want to verify. Okay, let's suppose relative to that yes. If you introduce non-determinism, you're adding more behaviors or allowing more behaviors. Okay, if those behaviors are not relevant to the property that you care about, okay, these symbolic model checkings and using SAS models are amazing. Okay, you don't need to care about those behaviors. Okay, so you're right that you will be adding behaviors when you introduce non-determinism, but if they are irrelevant to the property that you're verifying, it does not matter. Okay, and if you introduce non-determinism, sometimes the formula to represent the transitions can be even more compact. Okay, so it is the answer is not so obvious. Okay, so it can be more compact, and depending upon the property, it can even save. It can help. Yeah, but that's a good question. Yes, yeah. Any other questions? Yeah, I was about to say that don't worry if you don't have any. You have to look at some examples and try some examples out. Some of it is, yeah, there's a lot of detail in here, and unless you look at it, we will be doing. That's why, the way I've done is I've kind of informally introduced all these things, and I'm making you do problems on new SMB right away. Okay, even with this informal introduction, without even talking about how exactly model checking works. Okay, but that will give you enough. I'll assign you enough problems, exercises for you to actually do some examples and then feed it to new SMV, and then get the thing. So that will, very soon you will start feeling quite comfortable, and as you get acquainted with that thing. And that's why I'm doing it in this fashion. The real formalism starts with temporal logic. Okay, that will take another 2 or 3 classes. But you should not shy away from working examples out. Okay, and that's how that you get most out of this course. Any other questions? Thank you. I'll see you next week. Bye-bye.
Bye.